When we do acid-base titrations, we are reacting an acid with a strong base to form the conjugate base plus water, or we're reacting a base with a strong acid to form the conjugate acid plus water. Notice that I have designated the strong base as OH minus and the strong acid as H3O plus. This is because any strong acid will completely dissociate in water to form its conjugate base and H3O plus. So if this is a strong acid in water, what actually exists in water is H3O plus, and that is what is acting as an acid. Likewise, if we have a strong base in water, we know that it completely hydrolyzes the water to form these the cation plus OH minus. And so if this is a strong base, the thing that we have in the water that is acting like a base is this OH minus. Thus, when we have an aqueous solution of a strong acid, we will represent that as H3O plus. And when we have an aqueous solution of a strong base, we will represent that as OH minus. Any reaction of an acid with a strong base or a base with a strong acid will go to completion. So as long as I have either a strong base or a strong acid in my reaction, I can imagine that those reactions go to completion. And these are the reactions that we use when we do titrations. Notice that as I react the strong base with the acid, I am changing the amount of acid and the amount of conjugate base in my solution. And when the ratio of conjugate base to conjugate acid changes, the pH of this solution will change. The other way to think about this is that I'm starting with an acid and I'm adding a base, and so I will be increasing the pH as I add the strong base. Conversely, if I have a base and I'm reacting it with a strong acid, I'm starting out with a base, so I'm starting at a high pH. As I add the acid, I expect my pH to decrease as that acid is added. So we can keep track of the pH as we do these reactions. So if we think first about the acid reaction with a strong base, and we imagine what would happen to the pH as we add strong base, we would expect that we will start with a low pH because we're starting, when we have 0 OH minus added, we're starting with all acid. And so we will start at a low pH, and as we add the sodium hydroxide, we would expect that pH to increase because we're making the solution more basic. At some point, it turns out that pH changes dramatically and then levels off around 12 or 13 pH units. On the other hand, if we look at the base with strong acid, and we imagine what happens to the pH as we add H3O plus, we would expect that we would start with a very high pH because we're starting with all base, and as we add the H3O plus, we make the solution more acidic, and so we would expect that that pH would decrease and then decrease dramatically and then level off. So our base with strong acid titration as a function of pH would look like this, and our acid with strong base titration would look like this. Here is an example of a pH titration curve for a particular acid, weak acid. We'll just call it acid A. Let's take a moment to imagine what's in our beaker at every region on this titration curve. So when we start out, when we haven't added any sodium hydroxide yet, any strong base, so the volume of base added is 0 at the beginning, we're going to have in our beaker mostly water and our weak acid. Our weak acid is a weak acid, so it's going to dissociate in the water, but not to a very large extent, and so it's mostly going to be acid with very little conjugate base and some H3O+. The reason that this pH is below 7 is because we've made some H3O+ by dissociating some of our weak acid. So our beaker has mostly weak acid and water with a little bit of conjugate base and some H3O+, which accounts for the pH that's lower than 7. As we begin to add sodium hydroxide, that sodium hydroxide is going to react with the H3O+ or react with the HA. You can think of it either way. If it reacts with the HA, it's going to remove HA from this solution, and it's going to form more A-. If we think about the OH- as reacting with the H3O+, then it's going to remove H3O+ from this solution, and Le Chatelier's principle says we need to make more A-. In either case, we're removing H3O+ from solution, and so our pH begins to increase. And so if we think about this region where we're in the middle and our pH is increasing relatively slowly, we would expect that in our beaker now, we're going to have, of course, water, we're going to have HA, but we have also made a significant amount of A-. And so we're going to have some ratio of HA to A-, and that is going to dictate the amount of H3O+ we have in the solution, and thus the pH of that solution. At some point, we've added enough OH- hydroxide to the solution that we have used up all the HA. So we keep adding hydroxide, it keeps removing H3O+ from the solution. That forces this equilibrium to go in the forward direction, making more A-. And at some point, we add enough that we've used up all the HA. Remember that we have defined the end point of a titration as the point where we have added enough strong base to completely react with the HA, with the weak acid. So in other words, when we've added a stoichiometric amount of OH- to the reaction, and all of our acid that we had in there originally is used up, that's called the endpoint. And we can see that if we get to the endpoint and we don't have any HA left to dissociate, that all the OH- that I add to that beaker now will increase the pH of our solution because there's no HA left to dissociate to form more H3O+. And so we get a big jump in the pH when we get to the equivalence point. So the middle of this jump is the end point or the equivalence point of our titration. And you can see that we can measure the volume of OH- required to get to the endpoint. You can also see that this endpoint has a pH that is larger than 7. So it is more basic than neutral. So when we get to the endpoint, we do not have a neutral solution. So what exactly is in our beaker at the endpoint? At the endpoint, We have, of course, water. We always have water. That's our solvent. And then we've used up all the HA and we've made A minus. So at this point we have water and mostly A minus in our beaker. But we know that the conjugate base, A minus, acts as a base. And so when it's in water, it's going to hydrolyze to form a tiny bit of the weak acid plus OH minus. And so the fact that it creates OH minus by this equilibrium reaction, the base in water forms OH minus, accounts for the fact that we have a pH at the endpoint that is higher than 7. When we go past that endpoint, we're just adding more OH minus to our solution, and so our pH just continues to increase until it gets to the point where you've basically just got water with extra OH minus in it, and so it starts to level off at the highest pH that water can achieve.